Hi everyone, this is Hamid Tebyanian from the University of York. In this short video, I'll talk about our recent research on generalized time-being quantum random number generator with uncharacterized device. This is a collaboration with Technical University of Denmark, and here we can see the author list. Let's start with randomness definition. A strong string of numbers, or in general events, are called random if they're uniformly distributed, unpredictable, and also trusted. The action of this guy is not definitely trusted. There is another important condition, which is independency. Each event should be independent from the previous event. So we can also add independency to the random sequence assumption. Why random numbers are so important for us? Random numbers have many applications in science and technology. For instance, simulation, gambling, and more importantly, cryptography. To show you the importance of random numbers in cryptography, I give you an example. Consider there are two people on Earth want to communicate through public channel. Let's call them Alice and Bob. Alice wants to send a message to Bob through public channel. Let's think of satellites. So if you send a message through this public channel, since it's a public channel, everybody has access to it, and a third party, or in worst case, eavesdropper, can intercept the message, read it, and possibly change it. An easy solution to this problem is combine the message with a random key with the same length of the original message, and then send the encrypted message to Bob. On the other side, Bob can decrypt the message by subtracting the random key from the received message. Distributing the key between two parties is another topic, which is called quantum key distribution, and it's out of the scope of this talk, but I'm sure you can find many talks about QKD in Qcrypt. There are mainly two types of generators, classical and quantum. In the first one, which is classical generators, the generation of random number is based on a deterministic phenomena, so it's predictable, therefore it's not secure. On the other side, we have quantum random number generator, which the generation of random numbers is based on intrinsic random behavior of quantum mechanics, and it's perfectly unpredictable, therefore it's a good source for generating random numbers. Generators based on quantum mechanics are called quantum random number generators, or in short, QRNG. Despite the fact that quantum mechanics theoretically can provide pure randomness, but there might be experimental imperfections or some correlation between the devices and a third party or eavesdropper, which can introduce some errors in the system and make the system to be predictable. For instance, consider QRNG. It consists of a laser which sends polarized single photon to polarizing beam splitter, and then we have two single photon detectors. So consider the source is controlled by eavesdroppers, so she prepare entangled state, keep one, and send the other one to the measurement stage. The user perform a measurement, he or she gets click here, so the process seems random, but because Eve has the other pair of entangled state, so by performing measurement on the entangled states, she would know the outcome of the system. So there's no randomness actually in this quantum random number generator. So it's really important to study the setup and then characterize it. So in a project called Qcrypt in the UK, we try to work on partners' QRNGs and try to characterize and find out how much quantum randomness we can generate from each partner's device. So for more information, you can visit the website, which the link is here. Okay, so quantum random number generators in general can be divided into three categories. Device independent, which there is no assumption on the device's performance, and it usually based on violation of Bell type game, for instance, like non-local game, like Bell type inequalities. They gives the highest level of security, but at the same time, it's so complicated and slow. It is so complicated and it is slow. On the other side, we have a trusted device, which there's no assumption on the devices. It could be fast, easy to implement, but the security is so slow, as I show you. The security is so low. The same example I showed in the previous slide. In the middle, we have semi-device independent, which based on the needs of user, and we can make some assumption on the devices. So this semi-device independent gives a good trade-off between security generation rate and ease of implementation. This protocol, the one that I want to prepare, and this paper is based, is a semi-device independent quantum random number is a semi-device independent protocol based on prepare and measure scenario, where there is an input to the preparation stage, and the preparation stage is a gray box, means that we have assumption on the preparation stage, which we bound the energy or overlap state, while there's no assumption on the measurement part, so it can be seen as black box. To give you an intuition how this assumption works, consider two coherent states represented by these two poles here. When they're well separated, it's easy to distinguish them. But consider when they have high overlap. They become indistinguishable. Consider measuring a set of coherent states with high overlap and getting click here in the intersection area. It is impossible to understand what is the source of this click. This ambiguity in measuring an orthogonal quantum state is the randomness source of this protocol or this QRNG. In this QRNG, we try to use time encoding scheme. So it means that we place Bitcoin states in one of time beams. For instance, we can define like n time beams, and we can place one, two, or more number of Bitcoin states in one of the time beams, and we make sure that all states have the same overlap. Let's give you an example. So for instance, we can have one coherent state in a 4 time beam case, and so we can remove the rest. And there are 4 possible combinations. So the Bitcoin state could place in the first, second, third, and the last time beam, and we make sure that the overlap of all state is e to the power of minus mu, which mu is the mean photon number of each Bitcoin state. And for the measurement, because we use single photon detector, so there's a chance of getting click in the first, second, third, and the last one, which correspond to the each input. While there's a chance of getting no click in case when we have when mean photon number is really low, for instance, below 1. So there's high chance of getting no click. So this event, which defines here, is called inconclusive event, and the inconclusive event is the randomness, like it occurs randomly, so it's a randomness source of this protocol. Also, there are some errors. For instance, there's a chance of getting a click when there's no photons or the laser is off, but still there's a chance of getting click because devices imperfections. For instance, dark count rate, ambient light, or also afterpulsing effect. For afterpulsing effect, there's a chance of getting two or more consecutive clicks because like one click can cause a second afterpulsing click. So we consider all of this in our estimation. One might think, oh, okay, like we can place more Bitcoin states in these timings, and you can define more input. Yes, that's true. So with using Pascal triangle, we can define the possible configuration. So as you can see, the row represents the number of bins. For instance, like definitely 1 doesn't work, 2 doesn't work, and we can go for 2 inputs. The first column represents all the bins filled with vacuum states, and the last column also represents the time in which all filled with vacuum states. So we cannot use them because we cannot verify the overlap on. But the next one works, for instance, in 4th input case, which I explained. There are 4, 6, and 4 possible configurations, as you can see here. Set 1 represents this one, like the 4. There are 4 possible inputs. For set 2, there are 6 possible inputs. And again, for set 3, there are 4 possible inputs. And the same for the other number of inputs. But there is a problem here for set 2 because the overlap is mixed. So this is the easy solution. We can have a higher overlap, like a stronger bond, like we can say the overlap is e to the power of minus mu, and like we lose some randomness, or we can define 2 different subsets with the overlap for this subset is the same. And finally, we can define the possible number of outcomes, as you can see here. Then we can move to the experimental setup. Here is experimental setup. We have a continuous laser, and then state preparation, which is controlled by FPGA. So based on the number of inputs, we can define the inputs here, and then it goes to beam splitter. We monitor the power with power meter, which again controlled by FPGA, and if it's needed, we apply some attenuation in variable optical attenuator, and then everything goes to single photon detector. Time tag from single photon detector is converted to digital signals by time to digital converter, and again it goes to FPGA, and then we compute the conditional mean entropy and build our randomness extractor based on the conditional mean entropy, and we can extract some random numbers after in the post-processing stage. Here you can see the conditional mean entropy as a function of overlap for different number of input in the first figure. So we have 3, 4, and 5 number of input. These are theoretical prediction, and the dot shows the experimental result, which are in great agreement with the theoretical prediction. And also here you can see the subset 1 and subset 2 for the case of 4 inputs. And again, you can see the experimental results are in a great agreement with the theoretical prediction. And yeah, time is up. Here is the conclusion, and thank you for your attention. I will be happy to answer any possible question. So please feel free to send me email if you have any question. Thank you.